Images to kind of get us started and a reminder of what we want to do here. It's from 1938 from Astounding magazine. They had some really detailed ideas of how a vehicle should be designed to get us from Earth to Mars, and the whole thing's aerodynamic and includes lifeboats on it, so they're really thinking, plus artificial gravity. But let's not forget that Abbott and Costello got there too, so we can go as well. Some of the things we might see, we have our image there. We also have to understand that this has all been going on for a long time now, and we have Mars in art as well. I'd like to introduce my co-conspirator, is James H.L. Lawler. He's a chemical and nuclear engineer. He's worked with electrical propulsion since 1990. Numerous aerospace projects such as solar power for Mariner 4 and the original space plane, 1960 through 1965, and the National Aerospace Plane, the X-31, which was 1987 through 1990. Also has cryogenics, slush hydrogen, and plasmas. Worked with the superconducting supercollider, and is working with axial space-time physics with 4 major concepts. My name is Kenneth Hemmelgarn, professional engineer, mechanical design engineer with a professional engineer's license. I have a significant background in manufacturing processes and mechanical engineering. I'm a lifelong student of flight, engineering history, steam power, energy transformation, and control. Electrical propulsion is so far superior to any chemical option that it should be used for any deep space mission of more than 50 days. The mission must start from orbit. The very low thrusts make it totally unsuitable to achieve orbit. Classical rockets from and to Mars may be launched only about every 25 months to take the low energy Hohmann transfer ellipse. This is about 277 days. There is some slight variation, but the length of time is quite long. The typical chemical rockets, the payload is about 12% one way. With electrical propulsion, almost no launch window restriction. You can go and come when you wish. The time from worst to best position and best to worst power to weight energy supply varies from about 20 to 140 days. The velocity at mission half-time is so high that it is really not in an orbit. You can exceed solar escape velocity. The payload is fairly constant at 25%, but that can be a round-trip payload. The system requires 50% of the weight to be an electrical power system plus structure. That power can also be used while at Mars, which is a bonus. The weight ratios are roughly 25% payload, 50% power plus structure, and 25% reaction mass expended to get thrust. The key is very low but steady acceleration. The acceleration depends mostly upon the power per mass ratio of the energy source. But for now, we can expect about 1/100th G, which would be dependent upon a nuclear reactor, and that is optimistic. We can expect about 1/1000th of a G using current solar panels. Another advantage is that emergency mission changes are possible, and all it does is make the mission longer. You use the remaining fuel at full available power, and you still get home if you have enough air and food. It just takes longer. So getting started in low Earth orbit. Because of the need to transfer large amounts of materials into low Earth orbit, there needs to be an economical method of getting there. Payload into low Earth orbit. The system will be comprised of a land-based accelerator, an aerodynamic reusable first stage, probably similar to Sanger if you are familiar with that, a rocket-powered final stage with the payload. This is my second presentation, which will be on Sunday. This is a Mars transit assembly in low Earth orbit. delivered by the final stage off to the left. We'd probably use space-based personnel to do the assembly. Transit to Mars would start by rotating the vehicle so its thrust is in line with the orbit. As the vehicle increases in velocity, the orbit describes a spiral. Under a 100th G thrust, the spiral will be about 14 orbits until changing into an ellipse transit orbit to Mars. It takes about 32 hours. If we're using the solar collectors, we'll do that at 1,000th G thrust. We'll take about 140 orbits, or about 14 days to achieve the transfer orbit. At midpoint, the vehicle will turn 180 degrees and move the thrust towards Mars, and the deceleration until you get into destination. In comparison, we have a home and transfer orbit, which gives us a 277-day transit time with a 12.5% payload. It's only open for 14 days every 25 or 24 months. With an electrical propulsion to Mars using the low thrust, we have a 25% payload. We get a 325-day window every year. Our transit time will be about 40 to 140 days at 1/1000th G thrust, which would be typical of a solar-powered system. We get a transit time of 22 to 55 days using a 1/100th of a G thrust, which would be typical of a nuclear-powered system. So electrical propulsion systems, we would looking at solar panels, which have a long history of use in space. We have space station, we have orbiting satellite missions, and missions to Venus and Mars. Nuclear fission reactors, such as SNAP-10A, have been launched by America. The Soviet launches a 1.2 megawatt reactors that now power radar oceanic surveillance satellites, which are actually designed to pick up periscopes on the ocean surface, so they have to be pretty intense in usage of energy. The radioisotope thermoelectric generators have been launched. They're very inefficient and wouldn't be able to generate enough energy off of that. We also have Stirling cycle engines, also using the heat differential from the radioisotopes. There's also the GPHS RTG units, projecting 8 units to be used to deliver a 2 kilowatt thermal, generating about 100 watts of electricity. Using a comparable weight, our solar energy collection system is about 10% as efficient as a nuclear power plant. Now, using our generated electric, we can use a thermal arc jet, which is limited to thermal properties of the materials. We expect about a 1,000-second impulse from something like that. A magneto-hydrodynamic duct, a J Cross B, or a Vassimer. Vassimer is now being developed by Ad Astra, and we can expect 5,000 to 10,000 seconds of impulse. We can use an ion drive powered using materials such as cesium, mercury, xenon, argon, or CO2. We can go from 4,000 to 2,000 second impulse with that. A hybrid thermal arc jet and magneto-hydrodynamic duct is kind of complicated, but has safety fallback in that you can use part of it to get back should there be an issue with one or the other parts of the elements. This is an example of the difference between a 1/100th G acceleration and a 1/1000th G acceleration. Using Mars at conjunction with Earth, we would have about a 22-day transit time using the 1/100th G. If we use solar, we can get there in about 72 days. It's important to note, though, that if we launch off the tangent of the Earth orbit, we gain 19 miles per second. If we launch backwards, we're kind of losing 38 miles per second, and if we launch directly towards the conjunction, we lose 19 miles per second. Other transit demonstrating our 7 different launch positions that we could go from Earth to Mars. You'll note that at the top of the diagram there's a red shaded area. Launching in that window would give you a very near solar passage or through the center of the sun, which we wouldn't want to do. But otherwise, we have a full 325-day launch window throughout the year. And it would also make our former speakers' Martian visitation a lot easier to accomplish. In our other considerations to Mars, we'll be climbing out of a gravity well of Earth and sinking into the Martian gravity well. Turnaround is delayed from midpoint outbound and advanced to the midpoint inbound to Earth. Solar gravity and solar wind are small terms, but sophisticated programming will be needed to take into consideration all the gravity, solar wind terms, the sun, earth, moon, and the vehicles when calculating trajectory. Kind of expect this to be taken care of well in advance of any real mission. So a mission to Mars, what would that be composed of? We rather think this would be about a 5-ship flotilla. It would have 2 ships that are manned, 1 strict supply ship, 2 factory ships be landed on the Earth, on the Martian surface. I expect to produce CO2 that could be used for future missions, or could resupply one of the manned return ships, or to refuel ships destined for points beyond Mars. Multiple ships allow for redundancy for mission completion. Supply ships can be used to convey manned modules if necessary. Our next step would be to go beyond Mars. The asteroids are an average of 45 days away from Earth. Jupiter is 66 days away. Saturn, 88 days away. Uranus, 125 days away. Neptune, 157. Pluto is only 179 days away on average. We can reach any destination in the solar system in less time it takes to go for the home and transfer orbit to Mars. We can go. The solar system is ours. We have the technology to reach anywhere in the solar system. We believe that as a race, we must go out to the planets and make colonies, go to the stars, or we will go extinct. Our racial survival depends upon it. Our immediate return to space cannot be ignored. Anything tied to racial survival takes precedence over anything else. Delaying our leap into space is committing the worst crime possible, racial treason. We must recognize this and treat it for its overwhelming priority and requirements. The Mars mission transcends all local politics, even national politics. It is a racial issue to be faced by all men of every nation and every race and every belief. By its very nature, it demands cooperation of everyone. It literally is an issue that has no bounds. The Russians in particular have launched and used numerous high-power nuclear reactors and repeatedly tested and used electrical propulsion devices. Cooperation with them is not just advisable. Anything less would be idiotic. Ad Astra,